So I'm going to get started. So the first homework from chapter 2.1 is due on Wednesday, the 4th. The second homework from chapter 2.2 will be due on Wednesday, the 11th. That's next week, Wednesday. Name? And Joseph. Okay. If you have any missed any assignments, you can request an extension. Name?
Adrian.
Your significant figures worksheets are up here and graded. You can pick them up later. The quiz for chapter 2 will be on the 11th. I should have the quiz for chapter 1 graded by Wednesday. So those grades will be up. The chapter 1 and 2 exam will be on Monday the 16th. Much like quizzes on exams, you will get a sheet of notes. You'll need a calculator, but I'll have them you can borrow. So on Monday the 16th, we're going to spend all day on the lab. And our first lab will be today because of all the delays from the schedule and the snow. Should have been last week, but snow happened. So we will continue with chapter 2. Discussing acceleration. So acceleration is the change in velocity over the time it takes for that change to happen. Or, final velocity minus initial velocity over time. Oops. Let me get back to where I was. I jumped back by accident. Sorry about that. Which can be rewritten to solve for final velocity. In that final velocity is initial velocity plus acceleration times time. And that's very useful for computing final velocity. And it's possible to rewrite this to solve for any of the other ones. Initial velocity is final velocity minus acceleration times time. And time is final velocity minus initial velocity over acceleration. Now, for constant acceleration, if acceleration is constant, so for constant acceleration, the distance traveled starting from rest will be 1/2 acceleration times time squared. The most common case of this, which is what you'll see in problems, is for gravity for a dropped object. It's 1/2 g t squared for a dropped object, where g is the acceleration due to gravity, and that's equal to 9.80 meters per second squared. On tests and quizzes, I will give you that as a constant, and with the conversion factors and stuff. And velocity ends up being equal to g times t, because initial velocity is 0. And if you want, I can write out the equation, the general equation for position as a function with constant acceleration, but you won't need it for this class. Anyone want me to write that out so you can see it? It's just more complicated. Okay, I'll write it out. So in general, position is initial position plus initial velocity times time plus 1/2 acceleration times time squared. So because we're basically dealing with name. Basically, we're dealing with x naught will be 0, v naught will be 0. Both of those terms will go away. So you only need to worry about this case. Okay. So velocity is proportional to time. The distance traveled is proportional to time squared. Additionally, if you throw something into the air, on the way up and on the way down, at every height, it will be traveling at the same speed. Because the acceleration is pulling downwards the whole way, it works out, if you use that equation I just erased, but it works out that at every height, or if you throw something up, it'll come back to your hand at the same height, at the same speed. The ball will return to its starting point with the same speed it had initially. So V naught, the absolute value of V naught will equal V final. There's a minus sign in there. Because instead of going up, it's now going down. But speed doesn't care about direction. And it's actually true at every height. So here they'll be at the same speed, and here we'll be at the same speed. We'll talk about that a bit in chapter 4 when we talk about energy. So here we have a dropped object that falls a distance of 490 meters. And the question is, how much time, how long does it fall for? And then how fast is it traveling when it hits the ground? So the first question is for how long does it fall? That's asking for time. The second question is asking for final velocity. The initial velocity is 0 because it's dropped. The acceleration is g. And if you take distance equals 1/2 gt squared and solve for time, you get time equals square root of 2 distance over g for a dropped object. So I'll give you a little while to think about this, and then I'll show you how you work it out. So first step, we want to figure out how much time it takes to fall. Well, the distance it falls is 1/2 gt squared. So 2 times distance equals gt squared. 2 times distance over g equals time squared. So time is the square root of 2 times distance over g. So time is going to be the square root of 2 times 490 meters over 9.8 meters per second squared. 2 times 490 over 9.8 is 100. We take the square root of that. We'll find the time it falls is 10 seconds. So in 10 seconds, a dropped object will fall 490 meters. Now, in reality, it won't fall that far because air resistance will slow it down. But that's the theoretical distance. Now we can figure out how far it travels. Well, so how fast it's going when it hits the ground. Well, the final velocity is initial velocity plus acceleration times time. The initial velocity is 0 because you dropped it. Any dropped object starts with an initial velocity of 0 and speeds up. And the acceleration is g, 9.8 meters per second squared. So the final velocity is going to be g times the time, so 9.8 meters per second squared times 10 seconds, or 98.0 meters per second. So this will take 10 seconds to fall a distance of 490 meters, and it will be traveling at 98 meters per second. Now, in reality, a penny would slow down from air resistance well before that, but this is if it was like in a vacuum or something. So here we have a problem just about acceleration. We have a boat, but it's decelerating. Its acceleration is negative 1.5 meters per second squared. And it comes to a stop. So its final velocity is 0 in a time of 30 seconds. So the question is, how fast was it traveling initially? So we're looking for initial velocity. Remember, acceleration is final velocity minus initial velocity over time. You could rearrange that to be final velocity equals initial velocity plus acceleration times time, which you can rearrange to be initial velocity is final velocity minus acceleration times time. I'll let you think about that for a minute. So final velocity equals initial velocity plus acceleration times time. We subtract acceleration times time from both sides. We get final velocity minus acceleration times time is initial velocity. So we know our final velocity. We came to a stop. So our final velocity is 0. We know the time, 30 seconds, and we know the acceleration, negative 1.5 meters per second squared. So our initial velocity is 0 meters per second minus negative 1.5 meters per second squared times 30 seconds. So that is 0 minus negative 45, which is positive 45. So 45 meters per second. So here, a ball is fired upwards at 49 meters per second from the ground. So how long in time does it take to reach its maximum height when it has 0 velocity? So here, I'm shooting a ball up at 49 meters per second, and I want to know how much time it takes to reach its maximum height. And at its maximum height, I'm telling you that the velocity is 0. So I gave you the initial velocity, 49 meters per second, the final velocity, 0, and the acceleration will be g. And in this case, because g is pointing down and our starting velocity, positive starting velocity is pointing up, g will be negative 9.8 meters per second squared. If you use positive 9.8 meters per second squared, you get a negative time. And that doesn't really make sense. So we're going to use this equation in one of its forms to find the time. Well, you work on that for a minute or so. final velocity is initial velocity plus acceleration times time. We solve for time. Final velocity minus initial velocity equals acceleration times time. The final velocity minus initial velocity over acceleration equals time. So we'll be using this equation. Time is final velocity minus initial velocity over acceleration. Our acceleration is negative g, negative 9.8 meters per second squared, because it's pointed down. And in this case, we're taking up as positive. And so our final velocity is 0 meters per second. Our initial velocity is 49 meters per second. So 0 minus 49, and divided by negative 9.8 meters per second squared. Negative 49 divided by negative 9.8 gives us 5 seconds. And if you use positive 9.8, you get negative 5 seconds. And then you realize that you were using different signs for up and down. Yeah, your initial velocity was up, but acceleration is down. So you have to take that into account. So they have to have different signs. Now you can do this with g is positive, but in that case, your velocity, 49 meters per second, will be negative. Because then down is positive. And it's just, you can choose which way plus which direction is the positive direction. It's an arbitrary choice. So we have talked about linear motion. We've talked about velocity and acceleration in a straight line. Now, let's talk about what happens when we move in a circle. When you change direction, when you move in a circle, there is an acceleration because your velocity is changing. Your speed isn't changing if you keep going at a constant speed in a circle, but your velocity is changing. Quick demonstration. I spin this mass around in a circle, it is constantly accelerating as its velocity changes. The direction of its velocity changes. So since there's a change in direction, there is a change in acceleration. Now, if I'm spinning this around, when I'm spinning this around my head, what direction do you think the acceleration? Anybody have a guess? What? What direction do you think the acceleration is on this mass as it spins around? Like which way? So what happens with the direction, if you're traveling in a circle, the direction will be at right angles to the velocity. So when the acceleration and the velocity are in the same direction, you speed up. When they're in opposite directions, you slow down. If it's at right angles, you just turn and your velocity doesn't change. It will be at right angles to the velocity and it will point towards the center of the circle. So the acceleration when I spin this around, it's along the straight towards the center. So here, if you're going around in a circle, your velocity is this way, your acceleration is towards the center. Because this is, acceleration is towards the center or center seeking, it is called centripetal acceleration. This is centripetal acceleration. In a car, when you turn, it's applied by the friction of the tires with the road, for example. The car will remain in a circular path as long as there's enough centripetal acceleration, which will happen as long as there's enough friction. If there's not enough friction, you skid. If you make your car lose friction deliberately in a controlled manner, you drift. So centripetal acceleration, if you're in a circle, centripetal acceleration is your speed squared over the radius of the circle. So the faster you go, the more acceleration is required. And the tighter the curve, the more acceleration is required. Probably have experienced both of these facts. It's harder to do a tight curve than to do a shallow curve. And the faster you're going, the harder it is to make a curve of the same size. And that acceleration is proportional to your speed squared as you go in a circle. So the tighter the curve, the smaller the radius of the circle, the bigger the acceleration required, because you're turning more. And then the faster you're going, the bigger the acceleration. And it turns out it ends up proportional to your speed squared, because not only are you changing a bigger velocity, you're going around the curve, you're traveling around the circle faster because you're traveling faster. So the velocity ends up sort of going in twice. And this holds true for any object moving in a circle with radius r and constant speed v. And we can see the centripetal acceleration increases the square of the speed. And then as the radius decreases, the centripetal acceleration increases. So you can increase centripetal acceleration by either spinning things faster or decreasing the radius that they move around at, assuming they're moving at the same speed. So if we want to determine the magnitude of the centripetal acceleration of a car going at 12 meters per second on a circular track with a radius of 50 meters. So here, our speed is 12 meters per second. Our radius is 50 meters. So our centripetal acceleration is going to be speed squared divided by radius. That's 12 meters per second squared, 144, divided by 50 meters, which gives us 2.88 meters per second squared, which we round to 2.9 because two significant figures. So here it's written out. 12 meters per second squared is 144 meters squared per second squared. One of those meters cancels with the meters in the 50, and you're left with 2.88 meters per second squared. We can do a similar calculation to figure out the centripetal acceleration of the Earth as it travels around the sun. So the Earth is traveling at a radius of 1.5 times 10 to the 11 meters with a speed of 3 times 10 to the 4th meters per second. So centripetal acceleration is speed squared over radius, so 3 times 10 to the 4th meters per second squared. 3 squared is 9, 10 to the 4th squared is 10 to the 8 meters squared per second squared over 1.5 times 10 to the 11 meters. So we have 9 divided by 1.5, that's 6. And 10 to the 8 divided by 10 to the 11, that's 10 to the minus 3. So 6 times 10 to the minus 3 meters per second squared. So here we want to find, we have a merry-go-round that's 10 meters in diameter. And we have a child on this 10-meter diameter merry-go-round, and they're traveling at 1.5 meters per second. We want to find out what their centripetal acceleration is. So I'll give you a minute or so to work on this. And notice that is 10 meters across. Its diameter is 10 meters. And the equation calls for radius, the distance from the center to the edge. So, note, again, 10-meter diameter. So we want radius. That's going to be 5 meters, not 10. Because it will be half the diameter. The centripetal acceleration is speed squared over radius. Our radius is half our diameter. 10 meters divided by 2, 5 meters. So our centripetal acceleration is going to be 1.5 meters per second squared divided by 5 meters, which comes out to 0.450 meters per second squared. 1.5 squared is 2.25 divided by 5 is 0.45. Here, we have a mass on a string. We're spinning it, and it's feeling an acceleration of 200 meters per second squared, and it's moving at 5 meters per second. So the question is, how long is the string? I'm asking for the radius here. So if we start with centripetal acceleration and we want to find the radius, well, multiply both sides by radius. So centripetal acceleration times radius is speed squared. And so if we want to find radius, radius is speed squared over centripetal acceleration. If you wanted to solve for velocity, well, velocity is going to be the square root of centripetal acceleration. I mean, sorry, speed is going to be the square root of centripetal acceleration. So we know acceleration, we know speed, and we want to find radius. So centripetal acceleration is speed squared over radius. The radius is speed squared over centripetal acceleration. 5 meters per second squared over 200 meters per second squared gives us 0.125 meters. So that's a 12.5 centimeter string, which is, well, this long. But here, we're looking for speed. We have a vehicle has a centripetal acceleration of 160 meters per second squared, and it's traveling in a 20-meter diameter circle. The question is, how fast is it moving? So, centripetal acceleration, speed squared over radius. So centripetal acceleration times radius is speed squared. So speed is the square root of centripetal acceleration times radius. Radius is half the diameter, the 20-meter diameter circle. So the radius is 10 meters. So our speed is going to be 160 meters per second squared times 10 meters. all square rooted. That's 1,600 meters squared per second squared, which comes out to 40 meters per second. Shows these numbers to be nice. Now here's one about the centripetal acceleration of a moon. So Loon, which is the moon of Mungor, and it orbits at a distance of 2 times 10 to the 5th kilometers, and it completes an orbit every 10 hours. So here we need to figure out what speed is. We know the time it takes to complete an orbit and the size of the orbit. So we need to figure out what speed is to plug into our formula for centripetal acceleration. So here we need to think about the fact that we're dealing with a circle of radius 2 times 10 to the 5th kilometers. That takes 10 hours to complete. So we can use that to find our speed, because we have a distance and a time. So for this, our speed is going to be the total distance of an orbit, 2 pi times the radius, over the time it takes to complete an orbit. That's our distance, and 1 hour is 3,600 seconds. So centripetal acceleration is speed squared over radius. Well, we know radius, we need to find speed. Our radius is 2 times 10 to the 8th meters, because 2 times 10 to the 5th kilometers is 2 times 10 to the 8th meters. Because to go from kilometers to meters, we multiply by 1,000, or 10 to the 3rd. And our velocity, our speed is circumference over period. 2 pi times the radius over the time it takes to complete one cycle, one orbit. That's 2 pi times 2 times 10 to the 8th meters over 10 hours, which comes out to 1.2566 times 10 to the 9 meters over 36,000 seconds, which gives us 3.49 times 10 to the 4 meters per second. So 3.49 times 10 to the 4 meters per second squared divided by 2 times 10 to the 8th meters gives us an acceleration of 6.09 meters per second squared. Here we have a 1 meter diameter flywheel will break if the centripetal acceleration of the rim is greater than 8 times 10 to the 6 meters per second squared. So what's the maximum speed the rim of the flywheel can reach? So I want to get this flywheel up as fast as possible, and I want to know what my limit is. So this is one of those cases where you're solving for speed. So centripetal acceleration is speed squared over radius. So speed squared is centripetal acceleration times radius. So speed is the square root of centripetal acceleration times radius. Our radius is half the diameter, so our radius is 0.5 meters. So our speed is going to be 8 times 10 to the 6 meters per second squared times 0.5 meters. Square root. That's 4 times 10 to the 6 meters per second squared, or 2 times 10 to the 3rd meters per second, or 2,000 meters per second. So I can get the edge of this flywheel up to 2,000 meters per second before it tears itself apart. So here we have a car traveling at 36 kilometers per hour. Remember that 1 meter per second is 3.6 kilometers per hour. Has a centripetal acceleration of 10 meters per second squared. What is its turning radius? So here, centripetal acceleration is speed squared over radius. Radius is speed squared over centripetal acceleration. So the first thing we need to do is find speed in meters per second. We know the acceleration, it's 10 meters per second squared, so we need the speed in meters per second. So 36 kilometers per hour times 1,000 meters per kilometer times 1 hour per 3,600 seconds gives us 10 meters per second. 36 kilometers per hour divided by 3.6 kilometers per hour equals 1 meter per second gives us 10 meters per second. So our radius is going to be 10 meters per second squared over 10 meters per second quantity squared over 10 meters per second squared, which gives us a radius of 10 meters. So this car has a 10-meter turning radius in this case. So we have some time left, so I'm going to keep going. So some review. Speed and velocity. Velocity is a vector. Speed is a scalar quantity with only a magnitude. Velocity is a vector. It has a magnitude and a direction. Vectors can be represented by arrows. So here we have 40 kilometers per hour. Here we have 80 kilometers per hour. Here we have negative 40 kilometers per hour. Here we have negative 80 kilometers per hour. And the length of the arrow is proportional to its magnitude. Vectors can both be positive or negative. And we can add vectors by connecting head to tail. So here the distance is 2 meters plus 1 meter plus 2 meters plus 2 meters, 7 meters. While the displacement, it went 4 meters this way and 3 meters this way, which is a right triangle, and the direct line distance is 5 meters. And the direction for the displacement is sort of to the southeast. Now, sometimes we want to talk about relative motion. We want to talk about motion from different points of view. So here's an example. We have a train moving at 15 meters per second and a guy on the train moving at 1.2 meters per second relative to the train. So from his point of view, he's moving at 1.2 meters per second. And we want to figure out the speed of that passenger who's walking at 1.2 meters per second as the train moves at 15 meters per second relative to the ground. What speed this guy on the ground sees. And there's a pretty straightforward way to do this. If you want to find the velocity of object A with respect to position C, the velocity of object A with respect to B, plus the velocity of B with respect to C. So we have the velocity of the person with respect to the train, plus the velocity of the train with respect to the ground. And I like to write it in this way because you can sort of see that the T's sort of link together and you get the velocity of the person with respect to the ground. So here, 1.2 meters plus 1.2 meters per second plus positive 15 meters per second gives us 16.2 meters per second. But here, he's walking in the opposite direction. So you think of it as negative 1.2 meters per second plus 15 meters per second gives us 13.8 meters per second. So if the object, if the person is moving with the medium, so like a plane with a tailwind, you're going to add the speeds. If it's a plane with like a headwind, where it's flying into the wind, you'll subtract the speeds. Because one will be negative and one will be positive. So classic example is a boat on a river. So a boat on a river is traveling north with a water speed of 15 kilometers per hour. The river is flowing south at a speed of 5 kilometers per hour. So his water speed is his speed with respect to the water. So this is velocity of the boat with respect to the water. And this is velocity of the water with respect to the shore. But notice this is south. So this is negative if this is positive. So what is the velocity of the boat as seen from the riverbank? And what would the velocity be as seen from the riverbank if the boat was traveling south? So here's a picture. Sketching a picture is often very helpful in these cases. The boat is traveling north at 15 kilometers per hour with respect to the water. I used land. So I will match what I wrote. The velocity of the water with respect to land is 5 kilometers per hour south. The velocity of A with respect to C is the velocity of A with respect to B plus the velocity of B with respect to C. Oh, I did use one. Yeah. So the velocity of the boat with respect to the land is the velocity of the boat with respect to the water plus the velocity of the water with respect to the land. Now, the important thing here is just you need to keep your signs straight. So we're going to say north is positive. Then the velocity of the boat with respect to the water is 15 kilometers per hour and positive. The velocity of the water with respect to the land, because it's to the south, is negative 5 kilometers per hour. And if we add those together, we get 10 kilometers per hour. Because they're in opposite directions, you get less speed. So we have the velocity of the boat with respect to the land is 10 kilometers per hour to the north. However, if the boat was traveling south with the same water speed, then its water speed would be negative 15 kilometers per hour. The speed of the water is negative 5 kilometers per hour. The velocity of the boat with respect to the land would end up being negative 20 kilometers per hour, and the boat would be traveling 20 kilometers per hour south. So their speeds would effectively add. So when you're moving in the same direction as the water is moving, your speeds are going to add. If you're in opposite directions, they're going to cancel. So like if you were in a plane, if you had a headwind, that's the wind is blowing into your face. So that's going to slow you down. You'll subtract. If you have a tailwind, that's the wind is blowing from behind you. That's going to speed you up. And we'll add them. So we going back to the equation for acceleration. Any questions about relative velocity? So back to acceleration. Acceleration is final velocity minus initial velocity over time. For constant acceleration for a dropped object, distance is 1/2 gt squared, and final velocity is acceleration times time. Now, if you throw something, you have projectile motion. Here's an example. Projectile motion, when something is thrown, combines both straight line and vertical motion. You can treat the horizontal motion and the vertical motion independently. Vertically, it goes up and falls down, just like any other object you threw straight up or down. So if you fire something horizontally off of a horizontally projected object, the distance it falls vertically will be exactly the same as a dropped object. So A horizontally projected object will travel in a horizontal direction with constant velocity while falling vertically due to gravity. Horizontally, a projectile travels with constant horizontal velocity. Vertically, if it starts firing horizontally, it looks like, falling like that. So here we can see two balls that one was dropped and the other was fired sideways at the same moment. And this is a series of freeze frames. And you can see that over time, they're at the same height for every moment in time. So an object thrown horizontally falls at the same rate as an object that was dropped. So if you drop a ball and throw a ball horizontally from the same height, they'll always be at the same height. They'll hit the ground at the same time. The velocity of the horizontal direction doesn't affect the velocity and acceleration in the vertical direction. You can treat them separately. And if you project it at an angle, you have a vertical component where it goes up and falls down. And you have a horizontal component where it travels at a constant velocity horizontally. So if you throw a football, the horizontal velocity will remain constant. The vertical velocity will change. We'll start going up, become 0 at the peak, and then become negative. But you will actually end up at the same speed here as here. So the sort of problem for this, if I have a horizontal cannon at the top of a 12.25 meter wall, if I fire a cannonball at 100 meters per second, how much time does it take the cannonball to hit the ground? So remember, an object fired horizontally falls at the same rate as a dropped object. So we can use this equation for a falling object to figure out how much time it takes for the object to hit the ground. So the vertical distance is 1/2 gt squared. So 2 times the vertical distance is gt squared. T squared is 2 times the vertical distance over g. So t is going to be square root of 2 times the vertical distance over d. So 2 times 12.25 meters over 9.8 meters per second squared gives you 2.5 seconds, which gives you a time of 1.58 seconds. And if you want to figure out how far it traveled horizontally in that time, well, we can then take that time we just found and multiply it by the horizontal velocity of 100 meters per second. So the distance it travels horizontally is the horizontal velocity times the time. So 100 meters per second times 1.58 seconds means it travels 158 meters. Yeah. And so here, if a projectile gets fired from the top of a 44.1 meter pole at 5 meters per second horizontally, we want to find out how long it takes to hit the ground and how far from the pole the projectile is when it hits the ground. So in this case, same thing. The distance vertically is 1/2 gt squared. So time is square root of 2 times the distance vertically over g. So 2 times 44.1 meters over 9.8 meters per second squared, square root. That gives us 9 seconds squared. So time is 3 seconds. It's 3 seconds to hit the ground. So the horizontal distance traveled is going to be horizontal velocity, 5 meters per second times the time. So 5 meters per second times 3 seconds, 15 meters. And one of the things that will happen because of this combination of sort of vertical motion and horizontal motion, if air resistance is neglected, if you fire projectiles at the same speed at various angles, you will get maximum range at 45 degrees. And if the two angles add up to 90 degrees, the projectile will travel the same distance. So the equation for range is this. Initial velocity squared over g times the sine of twice the angle. You don't need to know that equation. What you need to know is that if air resistance is neglected and on level ground, two projectiles that are fired with the same speed at complementary angles, where the two angles add up to 90 degrees, will travel the same distance horizontally. And the maximum distance will be at 45 degrees. Let's say if you fire at 60 degrees or 30 degrees, both projectiles will travel the same distance. And this is actually a consequence of this equation. Because it turns out if you have two angles that add up to 90 degrees, the sine of twice that angle will be the same for both of them. Now, under real world conditions, there's air resistance, which means that the path is not going to be symmetric. And with air friction, the angle that you would fire something to get maximum distance will be less. You're not going to get the perfect thing at 45. With air friction, you'll slow down and you'll turn out to get the maximum distance. You'd want to be at a little bit lower angle because at a lower angle, you spend less time in the air and the air has less chance to slow you down, basically. And I think I'm going to stop there for today. And I will get started on